lecture. So because I think there's, following Descartes, that there's a res cogitans in addition to res extensa, which is not popular in physics, still has only barely begun to address the role of the observer. But following Descartes, I wanted an anthropic principle and anthropic cosmological principle. Holographic, you can also get non-locality out of that. Multiverse is self-explanatory, maybe. It's somewhat theological. Grains, worlds without number have I created, like grains of sand at the seashore. And I follow the Vigier and colleagues' model of tired light, where Hubble discovered redshift, not expansion of the universe. And they're in certain models of the vacuum and extended electromagnetic theory, there is good reason to suggest that there is an alternative for the Big Bang. As I said in the lecture, there are key elements of this particular holographic multiverse. And the essential ingredient is the structure of the least cosmological unit. There is some vague precedent for that, where I noticed really only one paper, primarily in a volume, edited volume by Kapatos. You may have had a co-op, I don't remember, where one of the authors talked about the size of the least unit. And he ended up having that be very close to Planck, which is what you would suspect for a standard model. Planck's stochastic virtual foam is the basement of reality. But, one thing I forgot in the lecture, most physicists believe that the extra dimensions, if they exist, are Planck size because we don't observe them. If you use a form, if you model your arrow of time with subtractive interferometry, imagine the movie theater model is best for this. You have the discrete frames of film at the projector, and then reality is continuous. And even a few centimeters per second is too fast for our vision. And the model of real reality is relativistic, and we're embedded it and made out of this material. So one metaphor for this is the two forms of screen animation. One, you have the little stick figure standing in the center of the screen, walking, in the background is moving. The other one is the background is fixed, and the stick figure goes off stage right and arbitrarily appears back together. And I think that kind of duality actually exists in this model. But you add a subtractive interferometry to this because we're relativistically, because we as observers, all of what we perceive is coupled to free space. And so at the point when you're going to see something else, it's subtracted out, like the frames of film in a movie, old-time movie theater. You don't see anything else. The main requirement out of a multiverse is this continuous state. That is essential, it's key. And the thing that is just as key is that in the hierarchy of dimensionality, with its continuous state, spin exchange, and dimensional reduction compactification process, that's the mantra of this. When you get down to near the 0th dimension, asymptotically, or quite reaching it, the union element of the least unit flips back to infinity. So all of this, I know it's very complex, and I've been very poor at putting this together in a rigorous way, but that can be done as we go along. But part of all of this is just to me it seems essential that we understand conceptually, so that we know why we're using the resonance hierarchy to look for there are no hidden cavities, QED cavities in the standard model. so we surmount the uncertainty principle to find the little periodic cavities that come in this model into the pockets of the higher dimensions, and they're limited because, as we talked about at the end of the presentation, uncertainty is a manifold of finite radius or finite dimensionality. And Elizabeth helped us refine that. It's probably going to be 4, 5, and 6 dimensions. If the way that a second doubling of theta space, anti-space occurs, it may have 9, but the redundancy may or may not still mean there's only 2 or 3 new spectral lines. We must, in conjunction with the continuous state model, it's the only way to surmount uncertainty. When you surmount uncertainty, we did review how, with the Stern-Gerlach experiment, arbitrarily, that we send out the continuous field along the z-axis, we get, as empirically demonstrated very well, we get the Copenhagen quantum uncertainty. So the key was to do something else. It has to be in a setting which the complexity of it to describe is a polarized, conformal polarized Dirac vacuum. When we add M theory to it, it also has a scale invariant copies, near symmetric copies of whatever the piece of matter is down here. And as we tried to explain, because of the creation, annihilation, and the boost from superluminal Lorentz boost from space to time to energy as part of extending bones into broken bones fail. It didn't work very well in 4 dimensions. But if you extend it to 8 dimensions or so, you can complete quantum theory in that sense. Kramer marginalized both of these, if they're marginalized because they're perceived, if they don't work, they don't add anything new. Kramer is marginalized mostly because they don't think it adds anything new. But this standing wave in the future path for a Kramer transaction aligns beautifully with the continuous state, especially as it applies to Kaplan-Almeida symmetry. So that's why I start the foundation of this model with Kramer. And as most of you know, Kramer derived his model from the Wheeler-Feynman absorber theory, which also didn't quite work in 3 or 4 space. Then we mentioned that to do the experiment in terms of the Dirac polarized vacuum, which is susceptible to, it has maybe one end of the continuum is the Dirac polarized vacuum, the other end is the Einstein energy dependent space-time metric. They use the difference in definitions to talk about different things, where Einstein is talking about warping and bending space-time and the energy that's associated with that at a different scale or a different way of talking about it. You talk about the Dirac polarized vacuum, which is susceptible to electromagnetic interaction under certain. As I mentioned, the primary evidence for a Dirac polarized vacuum is the Casimir effect. The lesser indicia of the Zeeman and the Aronoff-Bohm effect. Because extended electromagnetic proponents have also talked about tired light, it has been perceived to interfere with Gauge theory. That's actually a misnomer. If Gauge theory is an approximation suggesting there is new physics, in any case that it can be shown easily that it doesn't interfere with Gauge theory. So then we take the Sagnac effect, counter-propagating laser beams interfere in the small scale such that they interfere with special relativity. We take the Dubois incursive oscillator in conjunction with the Sagnac resonator. The size of delta T in the incursive oscillator can be the simplest way to do the experiment. The 4 orbits are the simplest, and then they discovered other ones, and then there are refinements. They originally assumed that the nucleus was fixed, rigidly fixed, and then they noticed that there's going to be a little wiggle in the nucleus, and so there are refinements to the spectral line. As I also said, I think the best indicia that we can have this kind of violation of QED is from NIST experiments. Not all of Chandler's experiments were done in NIST, just the most recent. The original one, I have to verify to be sure, I think he did the original one with hydrogen. And there was a suspected violation of QED, quantum electrodynamics. But it was too small that the physics community essentially ignored it. In 2012, and I just think that's the cleverest thing, to take a larger atom like titanium, strip all the electrons off at once, so and essentially you have a large hydrogen atom with one electron. And then, assuming that the uncertainty principle, you try to measure one thing, as soon as you touch anything, it decoheres and collapses the wave function, or makes it evolve to another state at the beginning of the and I didn't read the experiment very well, I haven't done it for a while, but whether one pulse or what you do, I suppose, is you just do a pulse and get your reading back as a cross section, I don't know how they did it. Doesn't make a difference how long before you do the next one. But because the titanium atom was so much larger, there's more space to collapse through. So that's why the artifact was large enough that the experiment was perceived to be much more successful, and there are, of course, some whispers in, oh, Nobel Prize. But of course, it's still not dramatic enough. Still, most 80% of the physics community still is skeptical, and that's the way it always is in the history of these things. But that is the best indicia that we can find new spectral lines in hydrogen. The fact that people at CERN are looking for them in a different way, they haven't started doing the experiments yet. That's just other people looking for higher dimensions. So to repeat, in conjunction with hydrogen, you set up your RF pulse Sagnac effect incursive oscillator resonance hierarchy to shape the electrons. I would guess you're going to shape the electrons in some way, no matter what frequency you use. So we want to shape them so that they resonate, they do some kind of spin coupling or spin orbicoupling with the nucleons. Then, and this is one of the things that remains that we haven't do, we need to figure out, and I hope the algebra will just make it fall into place, what is the size of the least unit? And that will give us the beat frequency of spacetime. There is no beat frequency of spacetime in the standard model. This only applies to this continuous state cosmology. There's no need to even look for a beat frequency of spacetime and reduce into a Planck as the basement of reality. You could try to maybe do something with the Zitterberg-Wagon or virtual particles to see if there's some kind of quantum oscillation, but we have a different kind of beat frequency in the rotation of these Riemann spheres. And since they're close packed, you've all seen the little toy where you have some little magnets on pins, and you take another magnet and bring it near it, and all the magnets jump around. So we're going to set up, according to that metaphor, we're going to set up, so the least cosmological unit is not one magnet on a pin. It's an array of however many we figure out we need to close back. Then we will finally, the final level of the experimental tier is our electron-nucleon resonance coupling must be done also in conjunction with the beat frequency of spacetime. And because there are some papers, there is a lot of work on cellular automata and programming the vacuum, I also think that if you apply some bandwidth to the vacuum, because of the infinite potentia, or the way that this can work, the close packing, the geometry of the close packing is such that any bandwidth will have some effect on the tessellation of the vacuum. So I haven't looked yet, and maybe Elizabeth knows. Nobody essentially knows how to couple the lower one to the space-time tessellation, but something about electron, nucleon, least unit tessellation in terms of this hierarchy with the incursive oscillator especially, we'll open and close. We will have, because, as I mentioned, the inherent hierarchy of this continuous state, because of an anthropic principle, or I think you can get around that, I just haven't done complete thinking on it, something about how a matter is created. If we're going to have, we don't have a full handle, we haven't girdleized sufficiently that we're outside of what a particle is. But with the unified field, we'll be able to girdleize outside of what a particle is. So we'll be able to observe the full creation of a particle. Right now we have just the tip of this iceberg in Minkowski space. So again, just to summarize and try to get out of this infinite loop that I'm getting into. In that sense, the experimental design is that simple based on these cosmological premises. Shake the electrons in conjunction with coupling to the nucleons in conjunction with the least unit rotations, time with an incursive oscillator. And this is in some of the books. I'm just glossing over things that have a fair amount of complexity that they need to be rigorously reviewed and understood. We will time the incursive oscillator, and this, because of the inherent, this continuous state dimensional reduction of a hierarchy, that's something that's going on behind the scenes all the time. It's inherent in this cosmology. With the movie theater, we don't see it because it's relativistic to us as free space observers. But because it is inherent in the process, we're getting half of this experimental design for free. It's built into the cosmology. So all we have to do is tack our, Feynman called this, when he first said how to build a quantum computer, he said use a synchronization backbone. People tried to do that, they decided it was intractable because what they did amounted to bilateral. They were still doing it in four space, so they'd take the line and all and do something in this part and this other part. They didn't get a real synchronization backbone. But there's an inherent in this continuous state structure, a synchronization backbone. So it makes it so much easier to open the resonance hierarchy. So the pulse, the RF pulses have to be timed when the gate is open, increasing, as we said, here's the lowest Bohr orbit, so we'll call it radius R. And then when you have the gate open, you're going to get R plus delta. And that R plus delta will be a slightly increased cavity. In the lower, we mentioned the first Bohr orbit is half an angstrom. The second one is 4 times further out, 2 angstroms. So we're going to get a 0.6 angstroms, 0.7 angstroms. I haven't done the calculations yet. Using the higher dimensional volume formula, it's too simplistic, but that will give us a good approximation. I'm pretty sure there'll be refinement. So before we submit, and this is work that any of us can do, is to finish calculating the volume of those orbits, which will give us a lambda, give us a wavelength. And then we will have to apply a Bessel function or something to the algebra to get the other. The beat frequency will tell us, if it's femtosecond, nanosecond, how the opening of the hole in space-time. But anyway, then simplistically, periodically in this continuous state hierarchy, the cavity opens, we send in our RF pulse, and it's reflected back into the NIST spectrometer, and then we will have a verification of what the wavelength of those spectral lines is. Hopefully that was a good overview. If there's a gap or something that's not understood, please ask a question. If not, I'll pass the microphone to others.
Okay. There are lots of terminologies which I would like to have explained. I'm going to just list them and then we could maybe start at the beginning. Least cosmological unit. Duality relationship between foreground and background. Dimensional reduction process. Resonance hierarchy. Cavities in the pockets of the higher dimensions. Uncertainty as a manifold. Mirror symmetry in this context. what means the rotations of the Riemann spheres. What is the beat frequency of space-time? That's perhaps enough, but you see there are many aspects of terminology which sounds very enticing, but for which I do not have any attached meaning, and so can't quite follow the form of the large-scale picture that you're drawing.
Okay, so tell me what's the first one we're looking at?
Yes, talk a bit about the least cosmological unit.
This, other than the Ham cosmology itself, the least cosmological unit is key to the whole thing. Without that, we have nothing. It's just it's a theory that can't go anywhere and has no meaning. In the history of my development of these ideas, some decade or so ago, I came across Kapatos' book where one of the authors, it's in the Ham cosmology, which you have a Ham textbook, which you have a copy of the textbook, reference to that paper and a little discussion of it. He came up with what he called the least cosmological unit, and he said its radius was the Planck. Well, I think he might have added a small little factor for oscillation, but it was essentially a Planck unit. I periodically looked at crystal structure, and they have, let's see what they call the least crystal unit. Unit cell, thank you. The unit cell. One unit cell builds up the whole crystal structure. So this terminology is somewhat arbitrary. I needed to have terms. I tried to have them correspond a little bit to existing terminology, but there is no such thing as the least cosmological unit in the holographic sense. So then, in order to move towards the beat frequency and the rest of it, and have a space-time vacuum that can be programmed, that can have cellular automata, this, as I mentioned, the simple drawing, which interestingly is like the logo for cross keys. I try to explain, we have at the center of it a vertex. That part should be okay. It's not just a standard model vertex, but we put the Witten string vertex in the middle because it adds that extra dimension that gives it a chance to wiggle.
When you say a vertex, you mean a fundamental interaction?
Do we have to say a fundamental interaction, Peter? If we have a fermion?
That's what I was going to do.
All right.
The vertex is the point where you do
All right.
interaction.
All right, but I could alternatively just talk about it in terms of metric.
Well, I'd say that it requires an action. In other words, it's a change from one state to another. However, normally it would be used in particle interactions, but if you had a fundamental space-time structure, it could be a change in structure of that space-time.
So I can get away with this by just saying it's the stochastic quantum foam that's the background of the standard model, and that would suffice, yes?
Well, I don't think that's what you mean, though.
Well, no, we can't throw away physics. There has to be.
No, I'm trying to understand. You see, what you said Capado said is what I said in the early 70s and the late 50s, that the quantum foam is a blank size. That wasn't accepted at that time. But you can quantize space and time as well as matter and energy and so forth. And like in the Lippmann-Schwinger equation, the independent variables are Q and E rather than X and T. So you can talk about a fundamental, Ilya Prigogine did too, a fundamental structure that is a discreteness, a very, well, I say it's a blank one, that is a quantized of the space-time vacuum, reality itself.
This is important because can we say an empty space, say between galaxies or consider that there's essentially no matter, there's no, we have to have, so the consensus among contemporary physics is unless there's some matter or interaction there, you don't have the vacuum, you don't have, we have a
Well, the
plenum
way I would
regard
look at
to
it is this: in order to make a measurement, a space-time measurement, I'm measuring space, so I have to bring up a ruler. I have to do a process of bringing up my ruler to measure this space. That takes matter and energy. And to run a chronometer to measure time takes matter and energy, probably a battery. So I don't see how to separate space-time as a fundamental reality from matter and energy, and that's what's in my presentation, that I treat a bunch of these variables as degrees of freedom or dimensionality. And so that they actually have to all exist at once. I can't have empty space and empty time because I can't tell it exists, and I can't have matter and energy without space and time because it has to be in that arena, as Wheeler would put it.
I think it's okay if we, as I like to assume, have a space of infinite potentia in the background, and it's all nilpotent, as Peter suggests. It could be doing nothing until we do something to it. So in that, I think I can get around or have that suffice to say, if there's an infinite potential, when we apply our measuring or any observation or something to it,
But
then
the potential is of something. There's a potential to be something. There's a potential to be matter and energy. There's a potential to be momentum. So if I had completely empty space-time, there's no way of measuring its existence. There's no knowing it without measuring it.
well,
That's where the observer
but
comes in
this,
at a
right.
macroscopic level.
Well, this experiment is a la observer, but if it's nilpotent, we can say that there's nothing until we do something to it. And doing something to it, it entails a measurement apparatus.
What do you think, Peter?
Although I agree with Elizabeth on this one. You can't have space without matter. It doesn't mean anything. You can't have matter without space. And nilpotency is the total condition of the universe. It's any object has to cancel itself with the rest of the universe. That's what that means.
I think nilpotency means that in order to have a geometry like a right triangle that is involved in squares, so that you could have a squared plus b squared minus h squared, the hypotenuse squared equals 0, then that, when you reduce that equation to a, b, and c, then you get a complex equation. You get an I in there. But that equation is based on a physical measurement of reality. The structure of reality has to demand, like, to make a triangle, it can't be just an abstract concept. There has to be a concept of something that triggers that ability to measure and make sure it is a right triangle.
To put it another way, if you think of a universe prior to an awareness or an observation, then there's no distinction. It's like the nilpotent background.
Right.
But when a distinction comes forth, then there's the awareness, the matter, the energy, space and time, the entire event universe has occurred there. It isn't like you can just do it abstractly, like you can think up the empty set as a mathematician does.
That's right, you can think of the empty set, but is there a parallel between that mathematics and an actual reality? And
Well, it is if you include the brackets and all the background that actually created the bag that is the empty bag.
Yeah.
And you in the process of drawing out that empty set.
Now, I would add one thing to your SAGNAC is the Dirac vacuum definitely affects on the proper solutions to the plasma MHD equation that I show using Feynman graph approaches, that to get the proper conductivity and conductivity of an actual plasma. The vacuum state electron-positron pair production comes in as a series of Feynman graphs to get the right answer. So to me, plasmas intrinsically and explicitly prove the existence of a vacuum, a direct type vacuum. And so that's another area besides the double laser experiment, the Saginaw experiment that points to the actual measurement of the qualities and quantities of the vacuum state.
I don't see this as a conflict per se. I think the way I've stated it has left out this background, because whenever in the lineage of this you decide to do whatever it is I've been saying for us to do, whether you have to add this nature of background definitions of the nature of the universe, it's still okay. I can move that up to the point when we're going to perform this action. I think these same hierarchical principles already apply at that point. But I think this is of critical importance to, especially from the physicist's point of view, to have that put into the picture. But would you then agree that if I move back or up what I was saying in the context that you just made, that it still relates in the same way?
I think I'm really more talking about terminology,
Yeah.
and I think that's what we were talking about, more terminology in physics here. And I would say the one question Lou asked, I think the least action or the least unit probably is more like a Planckian unit. But what do you see in that? I mean, what do you picture how that relates to relativity and particle physics? What is that?
It's a Planckian unit in the standard cosmological model, but it is not in the standard cosmology. And it's not a Planckian unit in string theory. We add string tensions, Planck plus string tension. So we already have a long precedent for something beyond the Planck unit. But in the standard cosmological model, yes, it stays at Planck. In 4 dimensions, it stays at Planck. But when I add this other hierarchical thing, then it is.
I think Planck's an n dimension. I think Planck can be extended to n dimension.
Then it can be used to make it useful. Planck.
Yeah, I don't think it's in contradiction with what you're saying at all. I think you're making a statement that might be kind of similar, but you do add the string tension point of view that the Planckian model per se, you need some additional components, the string tension plus whatever you're contributing to that concept.
Yeah, so this is a good footnote. In the standard model of a singularity or a vertex, it's rigid, it's fixed. The asymptotic continuous state to the reduction to asymptotic Planck means we have the Witten vertex, which is able to wiggle. So we don't get to Planck. We get down to Planck plus string tension. As I mentioned, current string theory has a fixed string tension, which I drew the little Planck and then a small circle for the addition. But in this model, it goes back to the original hadronic form where string tension is variable. That allows us to get that adds to the released unit rotation, so we get near asymptotic Planck, and if the Riemann sphere topology of it flips back to infinity. The reason for the Riemann sphere going from 0 to infinity is this compactification process from 12 dimensions down to 0. And that's an essential part of the least unit. We need the 12 dimensions, as I said, to surmount uncertainty and to have the whole hierarchy where all this, so it's a new view of reality beyond what we observe.
Can I ask a question?
Yeah.
When you draw the triplet for the least unit, why choose 3? Is that because of the Witten vertex here?
It's also, you can see how much Peter to be silly, I'll say worship the threefold symmetry. That's so a fermionic vertex. So that's the starting point. There's a quaternion vertex, the three IJK or XYZ.
Oh, yeah, I got what you're saying, but how, is there any way?
Well, but then
But then you could jump to a quartz because the SU3 works so well that maybe there's some reason that it's another scale up to get the particle physics at another hyperdimensional compactification cycle that 3 shows up as a 3/4.
if we're, and that's probably why the reason for it. As we develop tools of unified field mechanics, then yes, we'll start to be able to play with quartz. So I modeled that conceptually. I made the vertex. Some of the pictures I have the standard vertex that's fixed. Then I put the Witten vertex in the middle of it, which can wiggle. And then I put between, in the cavity, we talk about a brain, we talk about in the topology, brain, I'm sorry, I forget the term I want to use. Topological charge. So in the Calabi-Yau space, the cavity of the topology can have some charge in it. So the circles, and I said I derived them conceptually from the Broglie-Bohm quantum potential pilot waves, but they're control factors because this isn't a random evolution. Those control factors guide. I said there was inherent synchronization backbone. Those control factors of the symmetry guide that, keep the symmetry going. So adding Kramer and de Broglie-Bohm, extending to higher dimensions, Kramer and de Broglie-Bohm, you have with the superluminal boost from time to energy, those become control factors governing the evolution of this topology.
It's too much at once for me. De Broglie-Bohm to me is, looking at the Schrodinger evolution in terms of something like a pilot wave or a non-local potential. That's one thing. Kramer is a way of understanding the Brockett formalism by thinking a handshake between future and past, and is much more somehow formal, general, conceptual, not tied to the intricacies of the Schrodinger equation. So you're speaking on them in one breath, and it confuses me.
Calabi-Yau mirror symmetry in 6-9 dimensions has a left-right symmetry. And to me, that's the cap on Kramer's standard 4 dimensions. That build a tower on the left-right. The present as a standing wave of the future past. To me, you can just hook that in, and I haven't rigorously defined it yet, with Calabi-Yau mirror symmetry. You can, because of the annihilation creation of the...
Wait, let's slow down again. Calabi-Yau mirror symmetry is about the fact that different Calabi-Yau manifolds act symmetrically with respect to one another, so that parameters in one turn into, like by a Laplace transform kind of thing, into other parameters in the other one, and you get a perfect match. But you're in two different Calabi-Yau manifolds, each of which is its own string theory in the usual sense. You have some kind of dynamism which would put them together. In your theory, they would be interacting with one another.
Right, exactly. So I give them, that's one of the whole things where I, in a sense, criticize Elizabeth's 8 space that it was still reduced to plane. It doesn't have that kind of dynamism that kind of exists until you get this continuous state cycle, so that and we do know that they will transform one into another. That's string theory will admit that they.
I also have a 12-dimensional space, but the point really was with the complex 8 space, what is the least number of additional dimensions do you need to be Lorentz and Poincaré invariant that would accommodate non-locality? So the conditions on which I made on the manifold are not restricted are not restrictive of your conditions.
Right.
Because I also make in that superluminal boost paper a 12-dimensional space, which is certainly possible. It's just that I wanted to have the least number of added physics to get what I wanted. But I have also a 10 and a 12-dimensional space, so it isn't restricted to that.
No, I realize that, but I just add again this twist. As you recall, we go past Lorentz transformation. We now have a new transformation, so you need a 12-dimensional space to have a 12-dimensional transformation. So the Lorentz invariance is still another stepping stone. So I don't claim that this is rigorous yet, but I stick Calabi-Yau mirror symmetry on top of Kramer and give it. I think I've read enough string theory papers.
Wait, sorry, slow you down again, but what do you mean by on top of Kramer? Kramer says a quantum event is a handshake between the present and the past. We can kind of grasp that better than almost anything else.
Right.
Yeah, and then you say on top of Kramer we'll put the mirrors, the Calabi-Yau mirror symmetry. What's on top of?
We call it a manifold. Kramer is
How about the word addition to rather than on top of?
Yeah, I mean, I think of on top as it going up the ladder of dimensions, but Kramer's in 4 dimensions, and he has that symmetry, and then I tack on.
Oh, you're thinking past future is a kind of symmetry.
Yeah, same.
Right.
So
Yeah, all right.
I add those, and I realize that I have now, especially that I've skipped all that, but so I take the Kramer future past symmetry, and then whether typical string theory do it in that way. And I know I've seen where they can transform all of the 5 models of string theory, cycle them. So I don't see that there's a problem. So I tack on 9 more dimensions to give the Calabi-Yau left-right mirror symmetry the same properties. And that again is essential to the continuous state.
So you have new events that are handclasped between mirror symmetric symmetries.
Yeah.
When he says above a hierarchy, he really means in addition to, like I'm expanding the space of domain of action when I'm considering the shift, which means that he's expanding it to a hyperdimensional geometry above and beyond the Kramer or the Calabi-Yau space.
So that's important, these definitions. So
Well, this discussion open.
any questions or comments?
It's very restricted at the moment.
It sounds to me like your least cosmological unit could be, and this is very naive because I don't have, 90% of the terms you're throwing out here are like you kind of detached from my knowledge or something. It sounds like, and I do know Kafatos, I know personally, but you know, that you're talking about little quantized chunks of space. So I can visualize it as tiny little things. And it sounds as though you're thinking that if there are these multiple dimensions, you may be able, through some oscillations, to tear those chunks apart and there'll be holes in space.
Actually, only the lower ones are quantized. Once you get the tip of that iceberg in 4 space is quantized. At some point, then it's not quantized anymore. Okay.
I don't know about those higher dimensions. I'm just saying, you know, right now it sounds like I can visualize a couple of little points. You know. Now, when I do this, obviously it's 10 to the 30th times bigger, right? But you know, we're physicists. What the hell? And what you're kind of saying is that these things can be split apart, and there's a hole. How a hole in space, that I think is you're explaining with these higher dimensions, there's a hole in our space. Something will fall in or generate energy, which will. My question now is, it looks as though the experimental setup that you've shown is very much like nuclear magnetic resonance. So how do you get from that experimental setup to anything like the frequencies that would do the thing that you're talking about? I mean, it seems like there would be tremendous energy required for doing that. And oscillations of the kind that are accessible to us may just show us nuclear magnetic resonance again. But what kind of energies are you talking about in these oscillations?
I think they're very, very high energy. It has to go bigger than the Planckian because the energy for a Planckian unit is very large. The mass is 10 to the minus 5 grams. Forget what the energy is, but the Planck energy to get to such a small quantized or the sweetness in the space-time manifold would require definitely greater than L and C.
Right. So
This is
that's my
beautiful
question. I mean,
this is a beautiful question. I'm so glad it was asked.
Or maybe you want to do something.
Okay. Because I hadn't thought of this, giving that answer in this way. De Broglie matter waves. All we've done so far is find out 100 ways to demonstrate that de Broglie matter waves exist. And we haven't done anything else. This is, in a sense, starting to do something else. So instead, we're just using low energy RF pulses. And that's all that's needed. If you couple the resonance right, because of the nature, because of the unified field mechanical nature of matter and its creation and annihilation in this structure, and this will also be an end to super colliders. We don't need colliders anymore because with this method, once we can access this manifold of uncertainty, which needs more definition, we'll do a kind of cross-section through this that we'll be able to see the whole structure so much more easily. But the Sagnac effect resonance hierarchy will just use sufficient energy, and it's almost like an NMR experiment, except it's not applied to what NMR is, and we don't need a big magnet. It would be electron resonance, normal RF compatible with those energies, these small things
So
like
it's really
energy.
my path.
I don't even know your pattern.
I would have
I know
to
I'm describing.
ask what Kaufman said, which is, slow down, wait a minute.
I'm going to ask a really difficult question. Very simple question, but extremely difficult. What is your attitude to Occam's razor? Because my attitude is that I go for the least assumptions I can conceivably make about anything. But what is your attitude to it?
I see no conflict with Occam's razor because this is the minimum number of parameters that are required to go from. I mean, you could give that argument if you were a Newtonian classical mechanicist and try to throw out quantum theory.
No, I mean that you have many aspects to this model, and you need them all to work at once to get the model to work.
Well, remember I said the sign and synchronization background was inherent. It's half of it's already given to us for free. So that's already all working. All we have to do is do our little RF pulse.
I'm not talking about the experiment, I'm talking about the whole model. The whole model has got many different aspects, which are not conventional physics. Some of them are, but a lot of them aren't. So how do you be sure that putting them all together is going to get a real story?
Well, we have an experiment to test it. We're going to put them all together. But I see no conflict with Occam's razor because I'm talking about this as a whole cosmology. Of course, there's practically infinite.
What I'm saying, the normal procedure is to test one little bit at a time and see if that little bit fits in, and then another bit, and another bit. You build a whole superstructure. How can you test that?
This is a flaw in my personality. I've always felt, no, I'm serious. In my personality, the way of trying to describe things, I feel that unless I talk about helium cosmology, the continuous state, and the least units, and the reduction, that I felt that the only way that people need to understand it conceptually first. But we could just go straight to talking about the direct polarization resonance.
What I'm saying is that if you want somebody to test something by experiment, you have to put it in the form where you're not actually doing that much more than conventional physics as it now stands.
This is for us. This is for us. When we do the experiment, it's same like we talk about what we want to try to do with paper for science or nature. When we write the exact, none of this, 99% of this cannot go in.
Can I make some comments? You need to break the school. You need that? Do I need it?
No, you don't necessarily need it.
Yeah. Well, it's good. I'm hard of hearing and I appreciate it. I was going to say, at least I find, I have too many gaps in my background to compile the motivation for this experiment. So let's start at the back. If the experiment is supposed to produce a spectral line, that seems to me it must indicate that you imagine that there are some states between which an electron can do a transition. And evidently, at least half of those states are states that thus far have never been found in, say, hydrogen or titanium or whatever. So there's some states, and I find that a very plausible possibility. At least there are some metastable states or some transient states that might not have been found with conventional means of spectroscopy. Now, if there are some unconventional states, however we get there, with collaborative backgrounds and da-da-da-da-da-da-da, if there are some, then the experiment ought to be able to somehow or another pick them. And so the question in my mind is, perhaps we should address just how could we tickle whatever kind of states they are that's new and different from the way that states have tried to have been tickled in the past. I find it probably very improbable that a tabletop energy level experiment hasn't been tried already. Most of those, every cheap experiment has been tried by somebody and maybe not reported because it didn't turn out anything new. So you're fishing in very muddy waters.
No, like I said,
But that's not a criticism. That's just a warning.
cosmology may be a heresy, but I try to point out very pointedly that this is only plausible in this cosmology. So
The idea that any physical effect has one and only one explanation is very. There's usually at least hundreds of even maybe incorrect but plausible sounding explanation. But the problem usually with an experiment is to ensure that what you're proving is actually what you're trying to prove.
I'm not talking about the explanation, I'm talking about the context. We do the Stern-Gerlach experiment in a certain context. You can't do it with wider waves or some other stuff. The Stern-Gerlach, you send a signal out on the z-axis with a certain frequencies or a setup, and it splits into
the whole field of quantum optics nowadays does, I don't know, 2,000 versions of the Stern-Gerlach experiment in construction. That is, in its conceptual construction, there are parallels. They're done optically now.
right. So this is the first experiment along that avenue. But you need.
But it's still an atomic physics experiment. You're still looking for a spectral line. So at the end of the day,
we've been looking for those spectral lines for the last 100 or 200 years. We're not going to find any more spectral lines in four-dimensional quantum mechanics.
well, the experiment's going to be done in a
experiment.
You find them in the lab.
Oh, yeah, of course. Thank you.
Who has the 10-dimensional lab?
Well, I think a yogi, meditative yogi might have a 10-dimensional way.
Yeah, well, if you smoke the right stuff,
Yeah,
I'm sure
but,
we'll,
you know,
I'm sure we'll get there from here.
yeah.
Yeah.
Yes, you can get to 10 dimensions, but I don't know how many experiments you can do in that big.
Good beer will get you a couple of dimensions too.
But yeah, I mean, the experiment will either be successful or not.
Yeah.
And you don't need to include all this to say this experiment might be worth testing. Just do the experiment.
Let me get Ben Richards on this a little bit. Yeah, he's getting, by his model, he's getting a different slant on how to modify Stern-Gerlach type experiment that might look at the real space-time physical reality in such a different way. By the design of the experiment itself, that might find some new spectral lines, just because of his conceptual ideas creating this new direction.
Well, personal motivation is one thing, but if you're going to then back up the observations from an experiment and say they prove your personal motivation, you really have to have a very well thought out, well specified line of reasoning that the main purpose of which is to exclude all the other alternates.
Right, right.
And getting there from here, as Peter's trying to point out, if you have a theory, a motivation with many new hypothetical inputs, it's overly. I'm uncomfortable with it. I think, like Peter was saying, if you add one extra hypothetical input to already done stuff, then the experiments will test that hypothesis. But if you add 17, then you've got
You can't
17
test it.
factorial new.
Yeah, it's not possible.
Yeah.
Well, I think that's a little off the point. It's true, I've been talking about a forest, but ultimately, when we do the experiment, we pull out one tree out of that forest.
Yeah, but you'll only prove one tree, then you'll still not prove your forest.
You have to prove that all the other trees couldn't get there too.
I think it will be, if this model has any basis in reality, the first spectral line will be easy to find.
So in that case, you'll disprove your model if you don't find it.
Yeah,
Is that
Well,
the way
not
you
Oh, you have to.
He
You have
won't
to.
disprove it, he'll prove that he didn't find the spectral line. But that never precludes the theory, because he might not have looked at it right.
Yeah, it might not be an experiment.
So it really has to
Need
do
two
with the
more
whole
votes.
logic of
Well,
experiment
that's why I think
theory.
the other spectral lines will be more difficult. Those will be,
Well, I think
That makes it even worse.
You won't sell any idea to the scientific community, I believe, unless it's basically based on minimal assumptions. It's based on a lot, but you'll never sell it, never.
And a lot of these ideas are really shaky weight. When you start talking,
They won't sell everything now, unless you can say.
Kramer is a really, that's wild stuff, huh? I mean, you're really, you're introducing backwards action in time and all.
It's not just minimal assumptions, it's minimal number of different models. Pick a model instead of Kramer and Blobbiel and 5-dimensional and 8-dimensional models. Pick a single model.
as I said, I have always felt, it's inherent in my stupidity or whatever, that I feel the need, I don't know where it comes from, to try to explain every complete picture conceptually.
Yeah.
But after that, you can throw out this whole forest except for one tree. And so I could have, as I said, I don't see how I could have got away with it if I just came and started talking about the experiment. It's true, I could have got out all of Dubois' mathematics for the incursive oscillator, the Sagnac effect, and Dirac vacuum, and go there, but still, why should I find a spectral line under those circumstances? I'm only finding a spectral line if there's some additional cavity that opens up behind the manifold of uncertainty. And to say something about that, I think we can find a way of minimalizing that discussion.
But you've got to actually put that in such a way that you give the minimal assumptions needed to define that particular thing.
Well, that's what you guys are before. My talent is to come up with a fairy tale.
It's not out there, it's yours.
I never
Well, we don't have to convince anybody, you do.
Is this spectral line predicted beforehand by calculation?
Yes, well, as I said, I start with a simplistic formula for the volume of hypersphere in higher dimensional, the volume of higher dimensional hyperspheres. We get
What you have to do is expect out that one component that causes this spectral line to exist. And if you can do that, then you can actually maybe get a paper that somebody else can do the experiment, or you can do the experiment yourself and follow and actually test it out.
So let's go back to the beginning in a sense. So could I take Chandler's titanium experiment and say, if we do this in some kind of a Kaluza-Klein space,
What does that mean? We're gonna do it in the lab, not include a Klein space.
But we can actually do the theories of Kaluza-Klein space, develop a new piece of information.
Okay.
I'll buy that, yeah.
So I'll say it is our guess or whatever that the reason Chandler got a bigger QED artifact is because there is something.
You could sell that argument if you did it as Kaluza-Klein, because Kaluza-Klein is quite respectable, so you could put that in.
Well,
Say,
so that's fine.
one of the consequences of using it would be this, could we test it out? You could sell that.
Because as we talked with Elizabeth, and I kind of went back and forth, that all the spectral lines are measured in free space. So if we talk about a fifth dimension,
Yeah, that's all right.
Kaluza-Klein space, and say we want to make an argument for testing, for increasing the artifact that
It would be a new test of Kaluza-Klein theory as well.
Or some hypothesis
And
connected to right
it
from
ties
it.
in to the standard model because the twistor algebra of the Kaluza-Klein geometry is mapping over the spinor calculus of my complex H space, which is a subset of the standard model. So you can make a path that'll bring them across the bridge. That by making a tightly definitive theoretical hypothesis as to why you're working in this part of the RS spectrum with this particular titanium ionized for a certain degree under certain kind of gravity conditions or however. But yeah, I agree that I start the same way though. I start with a general concept in my head and then try to bridge it down into what I think I can bring the physics community to at least, the first step is where they throw tomatoes and then get them to, throw cupcakes and then get them to not throw anything, then you bridge that gap.
I think we can also, besides Bose Klein, there's a lot of talk in cosmology of ADS5 or 5-dimensional anti-de Sitter space, so you can tie the two of them together. So there are acceptable models for extra dimensions.
Why bring in cosmology?
We need to bring in dimensionality. We need to bring in dimensionality.
Dimensionality is not, cosmology is the discipline of theorizing about the origin and structure of the whole universe at once. But now we're talking about testing cosmology in an atom, so to speak.
Oh, he uses cosmology in a different way.
I was suspecting that, yes, that's what I'm trying to do.
Unified theory.
Pardon me?
I think he means a complete or unified field theory. And he calls it a cosmology.
Yeah.
So he would include quantum mechanics in the cosmology.
Yeah.
I believe that's correct.
Exactly, yeah.
And in a sense, I tend to agree with that, although it's not an understood term
No,
to mean that. Usually cosmology
Find a better
just means
term.
astrophysics.
Talking about cosmology is to
Our term reality is
the
a
street
cosmology
physicist.
of 4 dimensions, and that's how I would say it.
Cosmology doesn't use this 4 dimensions, but it isn't the study of.
I didn't say it was the
No,
study of.
well, you're saying you need to talk about, you're talking about that word just throws.
Okay,
throw it out.
He's saying a theory of reality is a cosmology, which is a misuse of usually what most people understand cosmology. So I'm a translator here.
Right.
I'm a translator. I wouldn't call it a cosmology. I would call it a theory of
A theory of space or
everything.
something.
But the more you say things like that, the more it puts people off.
Well, you can't put that in a physics paper.
No, it's
You have to
terrible.
accept it
No, you
in a
wouldn't.
journal, but he's talking about his concept that lead to this idea of this particular experiment. And so I support his idea of throwing everything on the table and then trying to refine it down. But I agree with your point about language. Because I couldn't understand Richard's use of the word cosmology. Now I do.
The more grandiose it is, the more...
It's really a theory of everything.
Well,
approach.
I also object to this concept of theory of everything. If you
Oh,
bring all
absolutely.
things together, it's not a theory of everything. Theory of everything would explain where those things came from.
Exactly, and that's why there is no toe.
So a lot of people go on about it.
Toes exist only on forms of life, but not in physics.
Well, they could do. It's not impossible, but those sort of theories are not theories of everything. It's a goal that we always go towards global memory.
That's it.
Well, that's arguable, but it's certainly not. But if you make assumptions about this space or that space or the other, then it's not a theory of everything.
That's why we're not the picture. Well, it's just a goal to completely explain.
That sounds like a sociological.
I don't agree with that. I think it's totally possible to
The so-called theory of everything will be another stopping place, and there'll be another.
No, I don't necessarily agree with that, but I think you've got to go from something minimal to get a theory of everything, not something maximal.
Or at least foundation.
Get a foundation.
You want to generate. There want to be lots of complex things that you totally generate that you don't know about except by investigating.
Go ahead.
You were mentioning that you will be able to calculate the wavelength or frequency that you're expecting for this. What will you do if this falls that you can't make it right?
Then if we need a better theory. the theory as it is predicts this manifold of uncertainty of a finite radius based on higher dimensional hypersphere volumes. So the mechanism could be different, the theory could be wrong, but the way I've been modeling it is I can make a simplistic predictions by calculating the volume of adding to the free volume, which we do our normal spectral analysis, adding a 4, 5, and 6 dimensional increment to get the 3-new spectral lines. That's the theory at the moment. If somebody else has another insight, I would think, I don't at the moment see any reason, have any parameters or logic for why it wouldn't be in conjunction with those increased volumes of hypervolumes from 4 to 6 dimensions.
So, do you have just a rough ballpark idea of what the frequency range might be with this
Yeah, I didn't finish those calculations. They're fairly straightforward and simple calculations. You have the volume of the first 4 orbit, and you can, and as I said, it's about a half a nanometer. You can then calculate the volume, the 5th dimensional addition, and then you would add that to the 3-dimensional, the 4th dimensional addition, which is the first one. You would add that to the 3-dimensional volume, and then you would do the calculation that gave you a wavelength. And those are very basic freshman chemistry issues. They don't have you calculate the standard orbits, but you can use all the same math and logic to calculate the wavelength of these others.
What is the extra dimensions of it? You can't add the volume in 3 space to the volume in 5 space meaningfully.
You're missing the whole point of the whole thing. Their Bohr orbit spectral analysis has been around for a couple hundred years.
I understand that.
So I'm saying in this cosmological model, to the 3rd regime, classical, quantum, and now unified field mechanics, behind the manifold of uncertainty, there are large size extra
Manifold has one meaning in auto mechanics and another in differential geometry. And
Well,
it sounds to me like the meaning you're using in it has more to do with auto mechanics than with differential geometry.
well, that's a good joke, but you
It's
know.
not a joke. You're using the
Well, it
manifold
is
in the
out
sense
there.
of a barrier.
Yeah,
I
it
didn't
is
mean it
out
as a joke. A manifold in auto mechanics is kind of a barrier. And this manifold-
Lou earlier said that Euclidean space is a manifold.
Well, Euclidean space is a manifold in differential geometry, but you don't hook up a manifold. You're using the term manifold, as best I can understand, as some kind of barrier or a boundary. And
Well,
a boundary of a manifold.
An
can also be a
automobile manifold is a thing of finite piece of junk.
Right.
And it has a boundary.
But it has a certain topology that does
Yeah.
the job.
Okay.
All right.
These spectral, sorry, are these spectral lines inside the inner orbit, the inside the volta? Will they be transitioned within, nearer to the nucleus, inside the orbit? Is that what you're saying?
My guess, because of the extra volume added, is they're going to be between the first Bohr orbit and the second.
Oh, right.
But they're in between only in the sense that when the timing is right, a little extra volume in the higher dimensions opens, so you get the volume of the lowest Bohr orbit is added to by delta whatever
And
from higher dimensions.
what I don't understand is how experiment actually can improve on what we're doing now to find these lines.
What we're doing now is a 4-dimensional quantum mechanics.
No, but when you do the experiment, you just measure spectral lines.
Yeah.
How can actually any calculation you do actually improve on the experiment that's done at the moment?
It can't.
Measuring those lines.
It can't.
Oh, so how are you going to do it then?
We've got a whole new model for the experiment based on additional.
No, but I mean, when you actually do the experiment,
What new action?
what are you going to do to
Experiment.
find these lines?
The whole thing of the experiment with our hierarchy from electron to nucleon to space-time least unit in the Dirac vacuum, that has, based on this rotation of these Riemann spheres, like I said, in an apple orchard or a graveyard, you have places right now because of the uncertainty principle, the tree is in front of us, we can't see beyond it. But in this cycling, we're driving the car by the orchard, open, close, open, close, open, close.
What way would you do the experiment differently to the way it's done now to find these lines?
The experiment now, they just energize hydrogen and then let it fall down and the line comes out.
So what
are you gonna energize this time?
What are you actually gonna do with the
We're gonna energize hydrogen, but it has to be done in terms of this hierarchy.
What
With this resident hierarchy.
So you have to
So
have.
what timing is that? What-
So yeah.
I don't know what the timing is yet, because as I said, we have to find out the beat frequency of the least cosmological unit.
so what you're
Which
expecting-
will be different depending on what
So what
atom we
you're-
use.
I'm fine with that, if that's what you need to do first. before you
I'm
do
not a
the
mathematician, I don't know how to post-pack the
So what
least
you're
unit.
expecting is to see these things coming and going, coming and going, coming and going. It's unbelievable.
What are you?
That's what he's expecting.
Sweeping,
Now we
what is
know.
he sweeping? Are you sweeping, are you turning a knob, are you turning voltage, are you turning a current?
Now we know what, he's expecting to
Why?
see lines that.
It's like an NMR
Yeah, but
experiment.
when they appear and disappear, he's changing something. What is being changed?
It is gonna be like an NMR experiment where the T1 energizes the hydrogen atom, and then the T2 is gonna have this extra.
I know how to do an experiment, I've done those, and I know you change it.
We're not doing that anymore, we already got.
Well, I know how to do that, but I don't know how to do what you want to do.
The same spectral lines of hydrogen we have.
I don't know what you want to do.
Well, you have to
Now we know what.
calculate, like a Bohr-Bessel equation. So
Yeah.
you're gonna have to say, I have a tunable, MRI, or
They're all tuned
MNR.
already.
So you have a tunable, but you gotta sort of figure out from his theory where to look, what spectral region to look at. And what I think he's saying is then if I'm tuned in such a way, I'll see instead of a solid spectral line for a particular state, I'll see what's coming and going. Is that right?
So Jim wants to
We won't
say
see it
something.
coming and going because we could only send it and have it coming, well, in a sense it's coming and going if we haven't let it quench and then fire it again. But,
So you want a false source?
Okay, Jim wants to say something.
go ahead, Jim.
Now, basically, you're taking an experiment, like finding spectral lines in the hydrogen atom.
Yeah.
What happens when you put it in a magnetic field? It splits lines, right? Yes, it splits lines, fine structure constant, all that. Well, you're trying to find something that's like a super fine construction constant. By instead of having a normal magnetic field, putting in from your experimental apparatus there, it looks like you're having a magnetic field this way and a cross magnetic field that way. If they're altered from an alternating current, you could possibly tune those to a specific frequency.
No?
Those two,
Yes.
to see if you get other spectral lines out of it. So like a super fine structure constant, much lower than the fine structure constant. And you're calling that super fine structure constant your minimal.
I think the fine structure constant would be a correction to the second and third.
Oh, a higher level, size-wise level. You're saying there's something
That's
smaller
why I
than
say the
that.
first one is
That will
gonna be
split it
easy to
further.
find.
That'll split the spectral lines further.
We should be able to get a rough estimate of the bandwidth of this least cosmological unit. When we go boom, then we will know where the other ones will be behind that. We will then-
Translate that into lab talk.
We have a bandwidth of the least cosmological unit. We fire our
And that's in a
pulse.
simple magnetic field.
So you're
A
increasing the
straightforward
magnetic field.
magnetic field.
You're increasing the magnetic field.
The frequency.
The variation.
I'm varying the magnetic cross.
Okay, all right, you're changing the frequency of the current going into the magnet.
I would say there's got to be a RF source that you're using,
Yeah.
plus a tunable electromagnet. So
Yeah.
you're changing both the magnetic field
Well,
strength.
the relation
and
of one to the
RF
other, the relation of one to the other,
frequency.
to a
Yeah.
specific frequency.
Has to
Yeah,
be tunable.
and then
That's
you
tuned
gotta-
across the
Yes.
You
spectrum.
gotta tune both.
Looking for that super fine structure constant. That's just a
That's
simple
what I
term,
think.
because that's what I'm understanding you're saying.
I wouldn't
You're just
define
putting
it that way, but
Well,
you can say it that way. I suppose.
I'm defining that way, so I think they understand it, because everyone probably knows what fine structure constant is. It's fairly well known.
We don't look at that.
You want to go past that and see if there are any more finer
Hyperfine.
structure levels, hyperfine.
They're not finer, they're bigger.
Frequency.
They're bigger.
Going in and out with a frequency.
Yeah, instead of a simple
Well,
magnetic
when
field, a
you
complex
mean fine,
magnetic field.
it's an additional split in the spectrum.
Well, yeah,
So it might be a
Well,
better,
it'd be very-
better
it'd be a
bandwidth,
magnetic field,
but
same
that's
concept.
what, there's two words for fine. Fine means, the fine structure constant means when you put the B field on, you get that additional splitting. What I think he thinks is the peak will be dominant and easy to observe, so that's a different word for fine, which means how wide or narrow
I'm just
the
using it in
peak
a
is.
very general sense, I'm not using.
Yeah, I know,
super
I'm
fine,
trying to
hyper fine.
define, communication.
Well, I'm just trying to use another word for words he's using.
All right, well,
A minimal measure.
If, I forget what the wavelength of the first spectral line in hydrogen, let's say it's 600 nanometers. Then if you multiply it times 4, the second spectral line is 2400 nanometers. So if this is 6, I'm saying there's gonna be some 7, 8, 900 nanometers. In the lower, beyond.
Behind the first, but before the second.
Right. So they're gonna be in the lower region between the first Bohr orbit and the second Bohr orbit. And, in that sense, saying they're tight-bound states is a misnomer. They're tight-bound states because of whatever, but if the cavity size actually opens towards the dimensions, then you get.
The immediate problem that comes up there is that region, that part of the spectrum, has been searched like crazy. That's why they know where the low one is and where the next one is. And they've been looking in there forever.
Yeah.
So now what are we gonna do different to see something that's in there? It's in there that hasn't been seen.
A specific frequency.
A frequency says what comes and goes at a particular frequency. That's the idea. Not at a particular frequency in the line, but a particular frequency at which it is. I think that's the idea.
Yeah. Get a broadband and look and see if you see any
Because
dimples in there.
because of the uncertainty principle, you're not gonna get that spectrum continuously. It's only gonna be cyclically in conjunction with the cycling of the least
So you need two
conformal
things, you need to know the frequency of the line, and you also need the frequency at which it is different.
Right.
If you had a broadband thing, it would be,
With particle accelerators, they're trying to get a high enough energy, trying to recreate your universe with a high energy, within a certain
Don't need
density.
to do that anymore.
Let me finish. You're saying instead of doing that, instead of going to high energy, go to a specific frequency that tweaks the same type thing. Instead of high energy,
I think
high
that's too simple, way of saying it.
yeah, if people understand that
I
it's
think it's
not.
along the right line. When BTA suggested tight-bound states, what did he say?
Oh, I didn't show that paper much. But I did talk a little bit about Baruch and Corbin, and they found these, they had to do with the Compton effect, but they would have been more in line with the Chandler experiment, so they would have found subtleties in the violation of these things. But I have extended that Vigier's model to larger QED cavities. I'm saying under certain cyclical conditions, the cavity is larger, the QED cavity is larger. And I'm also said that that's why I think the Chandler experiment worked. Because why the titanium experiment worked better than the hydrogen experiment? Because the radius of the titanium atom is that much bigger than the radius of the hydrogen atom. So there was additional time allowed for the collapse to occur. So they had time to show the additional energy.
What you're talking about is not a titanium atom, but a titanium hydrogenic.
Well, I left that out.
One electron.
I did say that earlier. The district all the
Right,
electrons
okay,
off the
then
wall.
I'm driving at a point here, and that is the attractive force to the nucleus is much greater than in hydrogen, because there's, what's the atomic number of titanium? 100 something, no? Anyway, it's gonna be much smaller than the hydrogen atom, because the force pulling the electron, pulling on the electron is much higher.
But it depends on how you energize the titanium, how you energize the electron.
If there's a
They off all the electrons,
hydrogenic,
so it's out on the farthest it's up on the farthest reaches of the titanium atom.
you
Because a lot bigger space than they've
increase the
energized.
charge nucleus, attracting a single electron, the electron changes. The lowest level then gets closer, and the speed of the electron goes up.
So we've established what experiment we're going to do. We've established the two measurements that we've got to be made.
Yeah.
So the basis is there, it's the details.
Yeah.
Same as how we did this
Right. So we want, we need a low inductive magnet. So we have broadband receiver in the range of the atomic spectrum, right?
Can you start with
Between the,
one
yeah,
double break?
I need some more coffee, so we.
Yeah, it's probably time for the
Keep our
next
excitement
coffee break.
alive.
What do I do? Coffee break, 10 minutes. Thank you all.
10 minutes.
No punches pulled. This is the time for hitting people, hitting me, especially. That was fun. That was good. Yeah, I like it. I feel we made great progress.
I think so. Very good.
Very interesting to hear.
I think I defended you a little bit,
Yeah, and I appreciate that. I might have to.
but I also
buy your
disagree with
cookie.
you completely.
Oh, I know, that's true.
Uh,
We are asking you for definitions as a form of defending.
I like that. I think that's a
what it is, though. They don't need.
you wrote down the perfect list.
They all need proper definitions. Yeah, I want a copy of your list. The list of books. Well, I have the word.
Oh, you're the.
Oh, yeah, my list of words. Yeah, that is essential, yeah.
That is essential.
I'll copy that. I'll scan that and send it.
Oh, it's perfect. Very good. Very exciting. I'm having fun.
Yeah, maybe.
Richard, I just finished.
Don't you leave your stuff.
No, I was calling you, but I've been on the phone with him.
Oh, I was reading fast for malnutrition, and I didn't know to get a copy for it. Oh, man, my eyeballs are rolling around in my head.
Then we're not gonna show it? No. I'm quite lucky that we've done in there. Well, who was the Lord? We have him or somebody. Somebody else was part of this. I got the whole last part of this. The last one. He wants to do it. If anybody's still around, we can do it.
Yeah, well, we tried to do this back the other day. I was there. People in Brazil showed me you just click on that and PowerPoint is right up on the screen. So we know the person it works. So that is still.
I do it all. We do it so. I'll have my camera. Yes. Very remote.